Today we intend to simulate Brinell hardness test, which would be simulated as an equilibrium problem. Hence, we are using static structural uh, analysis system for the analysis. And the first thing that you do is create a material model, which we have already done. So I have created a material model called mild steel, and I have inserted isotropic elasticity and bilinear isotropic hardening. So that is like the simplest plastic property. So we need this material model to be elastoplastic in order to simulate the effect of plastic deformation. So I've taken the Young's modulus to be 231 gigapascal. So we can switch the unit from here. And similarly, for the yield strength and the tangent modulus, we have chosen the unit to be megapascal and accordingly put the values. Values you can actually see on the screen, but I'll still say them out loud. So the Young's modulus we have taken to be 231 gigapascal, and we have also accordingly taken the Poisson's ratio to be 0.3. That is that value is typically for the Poisson's ratio is considered to be normal for elastoplastic metals. And for the yield strength, we have taken the value to be 347 megapascal, and the tangent modulus we have taken to be 778. So you can drag these properties from here. You can delete whatever are the default materials, that is say structural steel. You can delete it from here, from the list of materials, and you can create your new material. You can basically create the name, and in this case I have considered that to be mild steel, and then you can drag and drop different types of properties. In order for you to have an elastoplastic simulation, you need to have linear elastic or isotropic elasticity, or maybe even orthotropic or anisotropic properties, and some plasticity model as well. So both needs to be incorporated. So in elasticity, of course, you need to insert the elastic modulus and things like Poisson's ratio, or you can have any other combination. Any two of them will do for isotropic elasticity at least. Shear modulus or Poisson's ratio, bulk modulus or Poisson's and Poisson's ratio, and shear modulus and Young's modulus. Okay, so any two out of these four, that is Young's modulus, Poisson's ratio, shear modulus, and bulk modulus, you can use. Now different plasticity models are different. So this one is particularly linear, which makes the entire material curve bilinear, as the name suggests. The first part is the linear elastic portion, and this is the plastic portion. So this is the stress versus plastic strain part. So that is also linear. So for that you require only two properties, yield strength and tangent modulus, but different plasticity models will require different types of properties, because in many of the cases this curve need not be linear, and when it is not linear, then there are multiple inputs to define the nonlinear curve will be required, multiple parameters. But one thing probably would be common is that you also need to insert the yield strength. That means beyond what stress value the material starts having plastic deformation, that also needs to be incorporated. So we are mostly done with the engineering data, and today we are sticking with linear elastic material properties, and we'll close this one, save the project file, and move on to geometry. And we'll go with design modeler. So for that, design modeler is not currently the default option for Ansys Workbench. It used to be a long time back, but it is not. So what we would do is left click on geometry, right click there, and open design modeler. So new design modeler geometry is our move. Okay, now we will create our geometry. That in this case we are going with full 3D geometry. There are other ways to model this one. We could be doing axisymmetric, and we could be doing cyclic symmetric. Both are equally valid. Or we can also be doing, let's say, a quarter symmetric model. That is also possible. But today we are going with full 3D modeling. The symmetry models I would like to give you as an assignment, so you can do on your own. You can try both the hardness test and the tensile test simulation using type 1 axisymmetric simulation and type 2 cyclic symmetric simulation. So you can look into Ansys help doc for how to model a cyclic symmetric problem. So you can do that from there. Okay, I'll explain why I chose this particular example. It might seem that I'm just taking a basic experimental setup and doing simulation on that, but we get to learn few things, particularly regarding meshing and also regarding modeling rigid bodies in FE simulation. So in today we are not going to pick any of the planes and we are not going to create any of the sketches. We can right away go with basic geometry. So the first thing that you would do is to create the indenter. So I'm going to create a sphere, okay, and that sphere is going to be our indenter. By the way, we need to switch the units to millimeters that I should have done earlier. So I'm going to delete this one, switch to millimeters, and create primitive, and the sphere will have a diameter of 10 millimeters, not centimeter, 10 millimeters. And that means okay, have I taken centimeter as the unit? Okay, millimeter, and then create primitive sphere, okay, and we would take 5 millimeter as the radius. Okay, that's okay, but where do we place that sphere? I would like it to be placed the center, not at the origin, and let's say 20 millimeters above the ground, or 20 millimeters above the XY plane. Okay, that's where I would like to keep it. Before that, let me set my uh, isometric view properly. So yeah, okay, so I would like it to be 20 millimeters above the ground. Okay, and I'll explain the reason. Because I want to place my specimen, which would be a cylindrical specimen, at the XY plane. The base should be XY plane, and it should be 15 millimeters of thickness. And considering the radius of the sphere is 5 millimeters, I'm keeping the center of the sphere 20 millimeters above the XY plane. So let me generate the sphere. So this is going to be my indenter, and this is where I'll be applying the force. I'll create another primitive geometry, and that, as I mentioned, would be a cylinder, and that cylinder will have a base, or the origin of the base would be on the XY plane, and the height of the Achha, by the way, the radius of the cylinder should be, we'll take this to be 3 times the radius of the sphere. We'll take it to be 15. We should probably take more, but I think this should suffice. And the Z component will take it to be 15. So with that, it will just be sitting below the sphere. Okay, and like that we are done with the geometry. Now I'm thinking that we could be taking the cylinder slightly bigger. So let's just go ahead and change the radius to 20. Yeah, that seems right. Okay, I think we are done with the geometry here. So I'll close this window and move on to simulation. So we do open the mechanical window, and there are a few things that we need to learn there. So I've closed the geometry, and I'm also saving the file. Now let me move on to modeling. So this is where we would give the mesh control. We'll define the contact, we'll define rigid body, we'll apply the forces, put the boundary conditions and other things. Just one thing I forgot to do was I would like to divide this geometry into 4 segments, that is the specimen geometry into 4 segments for 2 things. One, for the sake of symmetry of the meshing, and number 2, for the ease of application of boundary conditions. Okay, so we'll divide that using XZ and YZ planes. Okay, so yeah, if that is what I'm going to do, then I don't need the planes. So what I'm going to do is slice by plane, and I need to select the base plane, so I'll go with ZX plane, and not all bodies but a particular body, and that particular body would be this one, generate. Okay, so I've created 2 hubs. I'll create 2 more, so another slice, and for that I'm taking YZ plane, apply, selected bodies, and I'll just select these 2 bodies. Yeah, this is what I did. I just clicked on one and simply dragged, and 2 of them would be selected while the left mouse button was pressed. That's how I dragged, and that way 2 bodies were selected. Apply and generate. Okay, so this should serve the purpose. I'm saving this one, and now I think I'm totally done with the geometry. And in my mechanical window, I'll just refresh the geometry. Okay, since I had deleted the default structural steel material and created a new material of my own, so by default none of them are assigned a material, so that's why there are question marks. So I'll do that now. Okay, so no assignment of the material, so I'll select all the 5 bodies and I'll assign mild steel, and even true for the indented as well, but then later on we'll make it to be rigid. Okay, by default connection would be defined, and that there are too many connections, too many contact regions, and I'm going to delete all of them and create one of my own. So I'm creating a manual contact region, and this one would be a rough contact. Okay, you can also go with no separation or frictional, but I'm going to go with a rough contact. Okay, so when a rough contact is closed, okay, that means that surfaces are touching and there is a compressive stress in the interface. There is no sliding possible. Okay, the rough contact can also be open, but when they are closed and there is a compressive load, then they, technically the coefficient of friction is infinite. That's what this means. Frictional, of course, can also be frictionless with a coefficient of friction equal to 0. And frictional, of course, represent the finite coefficient of friction, and frictionless, of course, is frictional with a coefficient of friction equals 0. No separation is where the contacts are always closed, but sliding is allowed without any resistance, and bonded, of course, as the name suggests, it's as good as welding, so no relative movement whatsoever in any direction. Now I believe Ansys will only allow you to select the rigid body as the target body, and all the deformable bodies like this 4 faces here, okay, are to be taken as contact geometry. So these red ones are the contacts and this blue one is the target, and we'll do some more settings. For example, the behavior we'll keep asymmetric, so that means no duplication will be created. By default, this is what Workbench does, not typical APDL Ansys, but in Workbench, because the software cannot decide on its own which body is to be considered a contact body and which one to be target, so it just creates a duplicate pair wherein the contact and target are switched. Trim contact, I would like it to be off, okay. We might as well let them be there, because anyway we are going to handle a large mesh count here. We need a good amount of refinement at the point of contact, which is literally a point here. Formulation, I mean, it is good as program control, but I'll still go with augmented Lagrange. Anyways, the program control will also use augmented Lagrange. So yeah, so this is good now. Now for meshing, I'm going with element order linear. I'll try to have hex dominant mesh. So and I'll also try to do mesh copy, or maybe even sweeping mesh I would like to do, and then I'll like to do mesh copy, okay, from one body to another and so on. So of course that would create wedge elements in the center, but that's fine. And I would like to go with linear elements. Okay, so I would also assign a global sizing so that the rigid body can also be meshed. Default size, sorry, no, element size, default element size. The sphere has diameter of 10 millimeters, so maybe 1 millimeter is the default size. How small is it? Yeah, this much small. Yes. And I'm first going to mesh this particular wedge, and I'll copy the mesh to every other wedge. I think I also made one more mistake. I should have selected these 4 bodies and made it into a part. So this correction I am doing in the design modeler, saving it, and I'll also refresh the geometry in the mechanical. Yeah. Contact region. Okay. So once again, some automatic contact region generation has happened, and I'll delete them. Okay. The reason there are question marks because once again they have selected the rigid body as the contact. Okay, so that is a no-no when it comes to APDL, but Workbench has done that. because it identifies as the body which has the, you know, smaller radius of curvature. So, or technically quote unquote the sharper object, and that's why it automatically sits as the contact body. And APTL has an issue with that. So anyways, we don't need this automatically generated contact, so we would delete these contacts. Okay, yeah, it is actually a rough contact, uh, but it is showing to be bonded. Okay, uh, show all bodies. Okay, and then show only this body. I would like to rename this one. Okay, so now I would be incorporating some mesh control. Okay, so for that I'm selecting a bunch of edges, actually these two edges. Okay, let me just make the global element size to be 2 millimeters. Okay, and I'll do one more thing. I'll create a new coordinate system, which is did I select a face? No, it should not be defined by geometry selection. It should be defined by the global coordinates, and the global coordinate should be the z value being 15 and x and y value being 0. That means at the point of contact. Okay, and I'm going to use sphere of influence for the mesh control. So the global sizing is 2 millimeters. Okay, actually, yeah, and I'm just using one control, that is sphere of influence. Sphere of influence, where is that? Yeah, sizing. Then select this particular face, sphere of influence, sphere center, the newly created coordinate system, sphere radius. I'm taking just the radius of the indenter. Should that be suffice? Should that suffice? No, I think I should take let's say twice the radius of the indenter, so 10 millimeters. Okay, and should this suffice? Yeah, probably it would suffice. And the element size that I would take is 0.5 millimeter. Okay, which is really small. Okay, I think I can also just select to be the radius of the indenter. That should actually suffice. That's what I think, because typically the indentations are much smaller compared to the size of the indenter. Okay, and now what we will do is we'll use a method. Okay, so for that we need to select a body. I'm selecting this body, and we'll use a sweep method. Okay, and element order, use global. Source target selection, I'll go with manual source selection, and this is the source surface. Okay, should I also go with manual target as well? Yeah, source and target. and I'll also select the target surface. Okay, free face mesh has to be quad and tri, no option there, and that's why I'm thinking, should I switch to higher order? Because if I am going with Tate elements, I would prefer quad elements, and if I'm sticking to brick elements, I would prefer lower order elements. Okay, the sweep number of divisions, I can take it to be, let's say, 10. Angular divisions, yeah. So yeah, 10 is sufficient. Okay. Okay, and no bias, of course. So let me just generate the mesh on this particular body. Yeah, so it created the mesh, but what I'm thinking, okay, it created the mesh. Okay, mostly they are brick elements, so I'm fine with this. That's skewed. Skewed is not desired, but if I were to get arbitrary quadrilateral elements anyway, because this is only in one particular corner there is mesh refinement, so it is mostly okay, I guess. There are two reasons I'm going with lower order elements. Firstly, the higher order elements with quad type are serendipity elements. Okay, and there are reasons we would like to skip that one. And number two is the mesh count, because with lower order element and mesh count are nearly the same. So we are pretty low with the number of nodes, only about 4,000 nodes. So with all the geometries being meshed, we'll only have around 16 to 17,000 elements. By the way, the rigid body will also be meshed, which is not being shown here. So let me just show all the bodies, but only its surface will be meshed because it has a contact with the remaining set of body. If it didn't even have a contact, there would be no mesh at all. Okay, because it would only be modeled with a point mass. Okay, but anyway, we have not inserted the density, so it also doesn't make any sense, because we are doing a static problem without any kind of gravity or any other type of body force. Okay, so now I'm going to use mesh copy. Okay, and my anchor body would be this one, and target anchors, source anchor was that body, and target anchors are these are the three bodies. Okay, so now um, what else am I going to do? I'm just going to generate the mesh and see how does it turn out. Yeah, that looks just about okay. Maybe one thing we can do is, with the target body, we can go with higher order element. The mesh is rigid anyway, so it doesn't go through problems like shear locking, volumetry locking, or any. I mean, that is also not the problem that the higher order elements go through, but uh, because the mesh is not going to deform or distort, so maybe for it will only increase the number of nodes. Okay, so I don't have to use a different size for this particular body, or maybe I can just use a different size for this particular body. So I'm going to insert sizing, select this particular body. Okay, and give a size, element size, how much? So yeah, 1 millimeter. So let me generate the mesh. Yeah, so with that, what is our node count? About 15,000. I mean, if we require, you can, at least we can reduce the node node size to element size to half for all the current sizes that we have taken. So one order of mesh refinement is also doable right now. Okay. Then let us move on to analysis, and in the analysis setting what we will do is auto time stepping, we'll switch it to on from program controlled, and the number of substeps, initial number of substeps, we can start with 100. Minimum number of substeps is also 100. Okay. Maybe initial number of substeps we can take to be 10,000. Okay, and that also we can take it to be maximum, also we can take it to be 10,000. Okay, should not be an issue with only a 15,000 mere 15,000 node count. Even if we had to go, let's say 100 or 1,000 substeps, okay, it is doable. Weak spring turned off, large deflection turned on. Okay, now we would like to make sure that it is properly constrained, and if it is properly constrained, then we can do some advanced setting also, where nonlinear controls, there we can use the full Newton Raphson method. Of course we can use, but not this one. I'm saying that the solver, we can take iterative solver as well. Okay, so what do I mean by iterative solver? Solvers which are of type other than, let's say, elimination methods. So a bunch of linear equations would be solved, a lot of linear equations would be solved. So where do we find that control? Stabilization, displacement, rotation, advanced, I guess here. Output control is not the one. Okay, solver type, yes, solver type. I'm deliberately going with iterative. Okay, but if any issue comes, it will be switched to direct, but I'm hoping there would not be any. So now is the time to apply all the boundary conditions. So first I'll pick the rigid body. For the rigid body, I cannot apply a displacement or a force. I'll have to apply a remote force or a remote displacement, which is only created using a remote point. So I'm selecting this surface and insert a remote force, and the force that you would be applying is 3000 kg force, and I'm just taking approximately 30,000 Newton. So I'll just not use the magnitude, but use the component. So it would be, the Z component should be minus 30,000. Okay, a downward force, as is confirmed by the downward arrow. And now once again we'll select the same surface, insert remote displacement. Now there would be a issue with constraints. Okay, if you apply a constraint in the same direction as the force, so we'll leave the z direction of displacement to be free. Every other will make it to be 0. So it is only allowed to move in z direction, no rotation, no translation, no other translation or rotation. Okay, now you'd say that we have already created a rough contact and there is a compressive force, so it would automatically not be able to move in any sort of direction. But yes, it's fine, it's still not over constraining, because both of those constraints are on the same direction. Now we'll apply some constraints to the specimen as well. Okay, so we need to constrain 6 degrees of freedom, so only 6 constraints we will apply. Okay, so first is a fixed, this is the rule that I follow. I pick 3 geometries. One is a line, one is a vertex whose dimension is 0, then one is a line whose dimension is 1, and one is a surface whose dimension is 2. So for the 2-dimensional geometry, I'll apply constraint in only one direction, for 1-dimensional in 2 direction, and for 3-dimensional, for a 0-dimensional in 3 direction. So basically I'll pick this vertex at the bottom of the specimen and make it fixed. So I'll just go and pick this vertex. Okay, this one right here at the bottom, I have picked that one. Okay, and I'll insert fixed support there, which means it is constrained in X, Y and Z. Okay, now I'll select this particular edge which is parallel to X-axis. Okay, and constrain it in Y and Z. So displacement in Y and Z. Okay, which means this line is not allowed to rotate either in plane or out of plane. Okay, so this vertex is fixed. About this point, this line cannot rotate about Z axis or about Y axis. Okay, so this is along X axis, so this line cannot rotate about either Y axis or Z axis. Okay, so that's why these two constraints are applied. Now next support that you would apply is to hold the specimen from the bottom. Okay, so remember how many constraints I have applied? 3 over here, then 2 over here, and then at the bottom, so 3 and 2, 3 plus 2 is 5, and then at the bottom I am just holding the entire bottom surface, okay, in the Z direction, so just 1. Okay, now for that there would be a normal displacement support, but yeah, the frictionless support, yeah, that's what I'm looking for. So for that I'm selecting this 4 faces again. I'm just pressing and holding it and just going on a circle and applying. Okay, which is basically preventing its motion in Z direction, plus or minus. Okay, so every force and every displacement have been applied. All 6 constraints are given. For the rigid body, for this one right here, okay, this only has 5 constraints. Okay, remote displacement, and in one direction there is a force. Okay, so I think we are good to go, and now let us try to solve this one. Okay, now you can see that this is the force convergence diagram. I believe they have also turned on the displacement convergence, but what I could have done is, from the analysis setting, I could have turned that off. Okay, in the nonlinear control. Okay, displacement convergence should have been turned off, because our problem is well constrained with the rough contact and everything. You'd see that the initial couple of sub-steps takes a bit of effort to converge. Okay, it's because initially the contact area is 0, right? Because it's a point contact, and as soon as the contact area becomes finite after a couple of iterations, okay, I mean also the time step size, initial time step size was of the order of 10 to the power minus 4. So when the load is properly applied and there is certain amount of deformation and the indented slightly sits on the specimen, the contact area increases. Okay, and thereafter the convergence is kind of becomes standard. Okay, there have been some smooth convergences over there. This is that is for 2 reasons, because initial set of deformations were all elastic in nature. Okay, that's why there is a convergence at every step, and later on plastic deformation starts happening. So once again it starts taking some more effort from the solver. That means multiple iterations. Other than that, one more thing is there. The time increment. The time increment was initially 10 to the power minus 4, but it has exponentially increased to 10 to the power minus 2 with subsequent convergences. Okay, so that's why it, once again, because the time step is much larger, it takes some more effort to converge. Okay, once again, when the area of contact further increases, okay, where substantial elastoplastic deformation has already happened, okay, for a large region, so what we can do is we can insert bunch of tracking. So let me go with deformation plot tracker, and let me go with stress plot tracker. Yeah, both of these are correct. I'm going with total deformation and equivalent stress. I could have chosen some other, but yeah, maybe directional deformation in Z direction I can choose. Okay, so I'll go with auto update, switch to automatic mode, okay, and next time there is a convergence, these two values would be updated. Okay, and this should give us some hint about how much the indenter has sat on inside the specimen. Okay, with the growing area, okay, the convergence becomes a lot easier. Okay, we know that the Brinell hardness number is directly related to the depth of penetration. Okay, so from directional deformation, we can figure out how much this rigid body has descended. Okay, and from there actually we can figure out uh, that how much is the depth of penetration by the end of the solution. Okay, while the solution was in progress, I realized something, that there is some mismatch between the mesh over here and rest of the geometry. And upon checking, I realized that although the mesh was being copied from, let's say this this body to all the other bodies. Okay, uh, in that previous example was but while it was being copied from the body in the opposite side, somehow the mesh got flipped from the upside went to downside, and vice versa, and therefore the mesh looks very different, and there is no mesh, there is a mismatch of meshing here. uh, and also I was checking the solutions were also being inconsistent, and therefore I made some corrections. The corrections being that I did use mesh copy, but only for these two bodies, that is to the left and to the right of the body which was originally meshed. So this is the body that was originally meshed. From there I am just copying the mesh to these two bodies, and for the body on the opposite side I am again using a sweep method, where I am manually selecting the source and the target, but I am not providing any face size or any sphere of influence of anything, because they are supposed to be sharing their topology. That is what happens when you create a part out of multiple bodies. Okay, they are supposed to share the topology, which means there are not two faces in contact. That is just a single face separating both the bodies. Okay, so the meshes should match, the elements should align themselves, and the nodes should be not duplicate nodes, but they should be interconnected. So basically the two bodies will share the nodes in the end, nodes being this corners of an element. So those nodes would be shared between the elements, shared between the bodies. Because of that, in this particular body, when it is being taken for sweep mesh, it is already under constraint regarding the sizing and the sphere of influence or everything coming from these two bodies. That is the one in the left and the one in the right, and therefore the mesh just turned out to be fine. There was no mismatch like mm, this case over here, and this one is good to go. And after that, some of the things that I did was in analysis setting. Of course, the solver was iterative. Weak spring was on, large deflection was weak spring was off, large deflection was on. In the solver, in the nonlinear control, I have turned off the displacement convergence. It has been removed. Moment convergence or rotation convergence would not be there because there are no rotational degrees of freedom associated with the deformable bodies, because they are not shell geometries, they are solid bodies. So there are no rotational degrees of freedom in the nodes of the deformable body. So that is not that is automatically turned off. And even if I wanted, I could have manually turned them off, but I didn't have to actually. And I have just turned on the force convergence, which would automatically would have been turned on, but I have still done it manually. And I have kept it in the default setting. Displacement convergence, as I said, I was removed, and the Newton-Raphson option was deliberately chosen to be full. So these are the changes that I made, and the mesh count with this type of alignment came out to be around 24,000. I'm using lower order elements, of course. So it was element count was about 23.5 thousand, and it was 24.5 thousand, the node numbers. And then I ran the solution, and the solution just went fine, with some red lines representing the bisection happening in between whenever a new region goes under plastic domain. So there would be bisections, and in the end, this is what I have got. Now these are not results, these are just solution trackers. So here one more modification I have made, and that modification was, if you recall, in the rough contact I had used augmented Lagrange method. Now augmented Lagrange method is a hybrid between something called a penalty method, which uses a contact stiffness and allows for penetration, and then there is another method which is supposed to be the most correct method, which is normal Lagrange method, which doesn't allow penetration, and it doesn't operate on stiffness basis, because it is the most ideal method, and in that case the stiffness is actually infinite. Now what is that stiffness? The stiffness is the practical example being that two objects, when they interact, one might deform the other, but one surface never penetrates the other surface. That doesn't make sense, right? Two volumes cannot occupy the same space in our day-to-day experience. So, but when it comes to mathematics, there are tricks wherein, sometimes in order to have a smoother convergence, for example, this curve right here, it's not that smooth. Okay, but for smoother convergence, what you would like to do is go with a penalty based method. Now augmented Lagrange method is wherein you in a penalty based method, that is what you are doing. You are actually allowing for a stiffness, so you are allowing some penetration, and therefore allowing for higher contact area and other thing from the get go. Whereas normal Lagrange, for normal Lagrange method, the initial contact area should have been 0. And that of course leads to a lot of iterations and a lot of convergence issues, and unless there is a special case, no one actually would use a normal Lagrange method. So of course we are using an augmented Lagrange method. As I mentioned, it is a hybrid of a penalty method and normal Lagrange method. So augmented Lagrange method allows for some amount of penetration. So unlike penalty based method, where the penetration can be of any amount, but in augmented Lagrange method there is some penetration tolerance, something called a penetration tolerance. I have kept it program controlled, and beyond that much of penetration it switches to normal Lagrange. So it is initially penalty based method, but once a certain amount of penetration has happened, which means certain amount of area of contact has also been generated, finite area, and then it switches to normal Lagrange, and then the convergence issues are not as high as it would have been with a 0 contact area. Now again, a penetration in this particular problem can, in this particular simulation that we are doing, can be of significance, because that means the deformation of the specimen surface would be less than the displacement of the indenter. Okay, ideally the indenter should descend as much as the top surface is deforming. Okay, so but if there is some amount of penetration, so the indenter penetrates the surface of the specimen and moves a little bit inside of the specimen, which means there would be a discrepancy between the deformation of the specimen surface as well as the deformation or the displacement of the indenter. Now, of course, there would be some amount of error if you are going with anything but normal Lagrange method. There would be some amount of error. MPC is not an option in this case, because this being a nonlinear contact, multi-point constraint would not work, which is typically reserved for bonded contacts. But the augmented Lagrange algorithm, if you are switching to either augmented Lagrange or penalty, so there would be certain amount of penetration. You cannot escape that. But what you can do is minimize that penetration. I mean, you can control how much that penetration would be, and that is by increasing the normal stiffness. Okay, as I mentioned, the ideal stiffness for which is in the case of normal Lagrange method, wherein there is an absolutely infinite stiffness. Okay, actually the stiffness term is not there at all, but if we were to evaluate the stiffness, that would be infinite, because there is absolutely no penetration. So unlike the normal Lagrange case, here the stiffness is finite, and some program controlled value is typically assigned based on the the stiffness of the underlying elements and other things. That is with the software, that is Ansys, that is what it decides. But you can actually use a factor. For example, if you are facing a lot of convergence issue even with an augmented Lagrange method, you can lower this stiffness factor, normal stiffness factor, and let's say you are getting good convergence, but you are anticipating a high amount of penetration, then you can actually also increase the stiffness. And in this particular case, as I said, we would like exactly the same amount of deformation of the, because it's actually the depth of indentation that decides the Brinell hardness number. So that has to be accurately measured. That means the descent of the indenter and the top surface, there should not be any discrepancy between the two. So that's why I'm using a high stiffness factor. In this case, 10 I'm using. So it would be using 10 times more stiffness compared to what it would normally use if this was left program controlled. I'm not leaving it program controlled. I could have, but I'm going with a factor. Okay, let me show you what do I mean by that. And I'm not showing any results here. All I'm showing is the intermediate results that I obtained from tracking. That is good enough actually. So this is what I got. So for example, this is the directional deformation. Okay, so as you can see, this this blue region is the lowest. So here we are plotting the Z deformation in the Z direction. So this blue region is the is a deepest region, okay, where the maximum descent has happened, and then it gradually increases to red. Now, one thing to notice, and that is that the red is not the extreme furthest point from the blue. Okay, so red lies somewhere closer to the blue. What does that mean? That means if I just scale the deformation, currently it is in auto scale. That means the deformations are being shown in true scale. Let me use an auto scale. No, so it's not in auto scale, it is in true scale. If I switch to auto scale, it would make more sense. Okay, and let me just remove one of the bodies. Okay, so basically uh, there is a valley over here, and next to that there is a peak. Okay, so basically it forms a crater like shape. Okay, and that means the place where the material descends maximum, right next to that there is a bulging. Okay, so this bulging is also physically observed when hardness tests are conducted. So one would anticipate that the maximum height, so this depression depression would e- mm, as it goes farther from the the point of contact, it will actually even out. Okay, and the maximum I mean uh, the highest point would be furthest from the point of contact, but that's not the case. The position immediately next to the point of contact is where the bulging happens, and then that gradually evens out. Of course, I'm showing it in a very high scale. If I slightly reduce it, okay, that would make more sense, or even the true scale is what is actually happening. So if you zoom in, you'd realize there is some amount of bulging that is happening, okay, right next to the indentation. So that bulging surrounds the indentation, and then that bulging evens out as we move further from the indentation. Okay, um, so that is one thing. Acha, one more thing that I want to show you is the this particular directional deformation. That is where I'm showing the deformation of the indenter. Now the indenter descends by an amount of 0.7 millimeter. Okay, and and the maximum depression of the specimen surface is minus 0.4 millimeter. So 0.4 millimeter. So you see that depression is not, that depression should have been the same as the descent of the indenter. Okay, now in order to have that more accurately modeled, that means the depression of the indenter being the same as the the descent of the indenter being the same as the depression of the point of contact. Okay, you would again have to increase this normal stiffness by much higher factor. Okay, probably taking 100 or 1,000 can give you more accuracy. Okay, but if you take 1 or less than 1, that is definitely going to be erroneous. Okay, apart from the directional deformation, I would also show you the equivalent stress tracking. Okay, so to the maximum equivalent stress that we have obtained is 577 megapascal, and of course this is true stress. Okay, uh, mm, so of course this is not a tensile test, and you cannot simply use the formula of true stress versus true strain over here, that formula that we learned in a previous video, that we cannot use here. But just remember, this is a true stress. Okay, the actual stress, because this stress right here is compressive in nature, the actual stress might even be larger. Okay, by the way, this is von Mises equivalent stress, so it is not the stress in the z direction. So other components of stress also have a play in this one. Okay, one more thing that I'm going to do is I'm going to hide this particular body, okay, to show you the contour. And the surprising thing to notice is that the highest stress is not happening at the point of contact. Okay, I hope you realize this is where the indentation, this is the exact point of contact, and this is the indentation, and this is where the slight bulging. Uh, uh, so the high stress is not happening immediately below the point of contact. It is happening in a, at least the equivalent stress. Okay, and for ductile materials, it is the stress that matters. It is the equivalent stress that matters. So that is happening in a pocket which lies somewhat below the point of contact. Okay, and that is also also at par with the experimental observation. So it is also at par with the theoretical derivations related to an indentation based hardness test. Okay. So after doing the indentation, if somehow uh, the stress can be measured, okay, that would have this type of profile. Okay. Okay. So, some of the new things that we got to know here was how to create a rigid body, and then a new type of meshing was used in this particular case. Sphere of influence was used, and that is actually that is actually necessary for this particular example. Let me show you why that is necessary. Let me switch from undeformed edge to showing elements. Okay. And you'd realize, although the element size was supposed to be really small over here, because the maximum deformation takes place over here, so they have undergone quite a bit of deformation. Okay. and uh, uh, and and is eventually been stretched to, you know uh, uh, higher extent compared to some of the elements that lies a little farther. Okay. uh, but one thing we can confirm that the stress is very small if you take the specimen size. Um, let's say the diameter of the specimen more than 3 times the diameter of the indenter. Okay. The stress is really small. Okay. Actually, it need not be the specimen size, but the region in which you are doing the simulation. Okay. And the maximum stress, or the lowest stress in this blue region is 15 megapascal. That is less than 3% of the maximum equivalent stress, which is happening that inner pockets that we have just seen. Okay. So I think I'm mostly done with this particular simulation. Okay. The assignment for you would be to try this particular simulation as well as the simulation of tensile test using number one, an axisymmetric model, and number two, a cyclic symmetric model. Okay. Both are quasi-static analysis, and in for quasi-static analysis, cyclic symmetry is can very easily be defined, okay, by a set of boundary conditions. But also you can use the cyclic symmetric tool that is there with Workbench. Okay. And you can only find that from Ansys help doc or YouTube videos, so you are free to do that. Okay. I just forgot to mention one more thing. uh, mm, we observed from the simulation that the descent of the indenter was 0.7 millimeters. Okay. Now let us try to evaluate the Brinell hardness number of the of the material, in this case mild steel, using the depth of indentation, that is the descent of the indenter. Okay. The formula for that is okay, the formula for that is BHM equals the applied force, in this case 3000 kg force, so it has to be in kg force, that is a unit, and then divided by pi the diameter of the indenter, that is 10 millimeters, and h the depth of indentation. Okay. uh, so we'll just substitute those values. So in this case we got 0.7, so we know all the values, so you can evaluate the Brinell hardness number from there. So 3000 is the force. Okay. And although there is a pi button over here, but I'm going to use an approximation. Okay, 3 point divided by 3.1416. Okay, and then divided this one by d, that is 10. So d and h should be in millimeters, and divide again with h, which is 0.7. If you do that, you get a value of 136. Okay, and I told you that the material properties that we used, that were for mild steel, and that actually we have obtained from doing tensile test. So these were the properties, by the way, in the engineering data. So the yield stress value and the tangent modulus value, these are the properties that we obtained by doing experiment tensile test on mild steel specimen. And now those tensile the properties obtained from tensile test we are inputting in this particular model to evaluate the Brinell hardness number through simulation. Okay, and we'll just see how accurate this one is. Okay, so if I go to internet and search for BHN, Brinell hardness number of mild steel. Okay, and this is the answer that I get. It is typically of the order of 120. Okay, so we are I can say we are very close. Okay, so we are not getting an absurd number. Somewhere I observed that that value typically lies between 120 and 130. For example, if I click this particular link, okay, that tells me mild steel has a Brinell hardness number of 130, and considering the value that we are getting is 136, I should say that we are very close. Okay, so that is the conclusion of this simulation. We are getting mostly an accurate, or maybe not even accurate, but a good approximation of the Brinell hardness number from simulation by using the material properties that we obtained from the tensile test.